The BSides DC 2016 videos are brought to you by clearedjobs.net and cybersecjobs.com, tools for your next career move, and Antietam Technologies, focusing on advanced cyber detection, analysis, and mitigation.
Okay, so this is Tales of Fails and Tools for Message Integrity. So I'm Jacob Thompson. I work for Independent Security Evaluators for a security evaluation and consulting company located in Baltimore. So we're local. A quick commercial break. So our company, we're composed of computer science academics, ethical hackers. We do all sorts of white box style security evaluations for our customers. So very much an attacker's mindset and so forth, trying to look at a product and tell them where the problems are and how to fix them and so forth. Back to the talk. So thinking about message integrity in terms of cryptography. So personally, I think there's much more of a focus on confidentiality, so AES and so forth, in the terms of, say, enthusiasm. But actually, integrity is just as important. And by integrity, I'm talking about two ways. One of them would be modification of data while it's at rest, sitting on a disk somewhere or in transit, like over a network. And passwords would be the second example. It's important to note, though, that in many cryptographic protocols, the ability to modify a message or tamper with a message can also lead to the loss of confidentiality. So I've often, especially earlier in my progression as a security person, in the scoping and attack surface recognition part of an assessment, they talk about, we use such and such AES for this, and they didn't have anything for integrity, and I have a habit of saying, well, like, how likely is it that anybody will tamper with that anyway? But it can be very important. And I think it's also more nuanced and interesting than confidentiality sometimes, just because a lot of the problems are not as close to being 100% solved as they might be in symmetric encryption and so forth, or at least to a degree. So the approach I'm going to take is I'm going to go through a tour of a lot of past vulnerabilities, past exploits in various projects, and the attack methodology behind them so that you can kind of see the ways in which integrity checking often fails. And then I'll close out with a review of best practices so that if you're a security analyst also, you'll have some things to think about as you do assessment. So we'll take a look at fails. So common ways in which, say, programmers or architects fail when they're designing a system. So I would say one of the most common is assuming that encryption of data also protects it from being modified. If not well, then good enough. So first example, and this is the worst case, stream ciphers and malleability. So remembering what a stream cipher is, so one-time pad, right, RC4. Basically, you have a key stream and you have plain text and you XOR them together and you get ciphertext, just as I show on here. So hello world, take the ASCII values, you have a key stream, you get data. So just like a one-time pad, right? Or it could be something, a PRNG generating key stream. Decryption is just the opposite. So biggest thing to notice, encryption and decryption are the same operation, they cancel out. So if you encrypt it twice with the same key, it's not twice as secure. Looking at how decryption happens if we've tampered with this message in some way, the important thing to note is flip a bit in the ciphertext, the same exact bit gets flipped in the plain text after it gets decrypted. So this is called malleability. It affects every stream cipher. So in a way, one-time pad might be the best for confidentiality. It's the worst for integrity, unless you have something else in place to protect that. So seeing that, let's take a look at some ways in which this might actually fail in a real system. So I made an example here. Everybody knows about client-side session management kind of being all the rage right now. So you have these RESTful APIs and load balancers, and you get a different server with every request and so forth. So a lot of developers have this idea, let's just store the session data in the cookie rather than having the cookie refer to it, right? So you do something like that. So I made a small web application. You have a session cookie. It's some encrypted and base64 encoded string, right? I've formatted it so that the layout of that cookie is an initialization vector concatenated with ciphertext that was encrypted in AES counter mode. So counter mode, just recalling, turns a block cipher into a stream cipher. So it is also affected by these problems. Looking at the plain text format of that cookie, it's JSON data, username is admin, and a timestamp. So the question is, using what we just looked at about malleability, could we flip is admin 0 to 1 without knowing the key, right? So looking more closely at the actual positions and layout of the cookie, you may not know what the key is, but if you have known plain text, you can determine the position of the bit where the 0 ASCII value could be flipped to become a 1. And we do just that. So look down at that is admin 0 line, and we can flip the ciphertext byte 40 to 41, knowing that from the ASCII values of 0 and 1, that causes it to become a 1. Does that work? Of course. So taking a normal request to our fake web application, we get you are not an admin, and presumably it won't let you do non-administrative things. If we tamper with that cookie and then re-base64 encode it, send it to the server again, we get exact same request, except now we are an administrator. So encryption doesn't protect integrity. If you have a chance to quickly copy down the URL if you're interested, basically demo.securityevaluators.com/integrity/stream. And then we'll take a look at another example. So everybody knows that about stream ciphers in many cases, but also block ciphers can also be affected by tampering. So CBC mode cipher block chaining is one of the more common and easy to do correctly modes of encryption. So it's often recommended is like if you have to implement it yourself, maybe do this. In terms of a formula, you have a special first block called the IV, and then you have encrypted blocks of plain text where during the encryption process you add this kind of noise term, which is the previous ciphertext block into the encryption. And then because it's a block cipher, you can only encrypt in multiples of the block size, so you might have padding at the end, which I've added in this case as well. So this might be a typical block cipher encryption of the string hello, hello world 3 times in the plain text. Decryption is the opposite process, except your IV and padding will be thrown away. Now, in stream ciphers, if we make some change to the ciphertext, it made the same change in the plain text, right? It was very easy to make modifications. Oftentimes, because of what is called the avalanche property, if you take within 1 unit of ciphertext in a block, you flip a bit, you have 0 control over what will happen to that block when it decrypts. But take a look at what happens in CBC mode. Let's flip that 6A byte on the second line to 7A. All right, that block that decrypts, when that block decrypts, you get noise, right? It's some random data because of that avalanche property. However, because of how CBC mode operates, that ciphertext will be, that XOR will happen, and notice we have a very controllable modification to the next block, where we change some ASCII value so that instead of an X, or instead of an H, we got an X. So that could be a problem. Now, if whatever application you're working with is very rigid about its data format, this is probably not going to work. If it's some special case, maybe it will. Another thing we can do in CBC mode is a cut and paste attack, where because a block can be moved around, as long as the block before it is correct, it will still decrypt to the same thing. So let's look at another made-up example to demonstrate that. So here I've made a Python program that is kind of a very boiled down demonstration of something that might be dangerous. So it starts, it takes 1 command line argument pointing to some directory, it does some kind of sanity check, and if that check passes, it does something dangerous. Maybe rm-rf/, if it were for real, or maybe it does a backup or something, right? Or upgrades a package. But I've made this is actually made in a very specific format for convenience, so that all the boundaries between CBC blocks will line up, right? But the core of this is this if statement at the bottom. If we focus in on that, then for demonstration purposes, this sanity check is always true. So if true, don't actually do the operation, else do it. So our question is, knowing what we've learned about CBC, given only an encrypted copy of this script and no key, is there a way to modify it so that the else block executes instead of the if? So you know what the script has inside it, and you have an encrypted copy, you don't have the key. So you can't do the straightforward modify it and re-encrypt it. Well, if we actually break that script into blocks, then we notice that what is a triple quote string in Python? Multi-line string literal, right? So this is in such a way that what if we could take this multi-line string literal, have it not end where it does, and move the end of that string to somewhere below the code we don't want to run, right? So I have abbreviated it some, but you see that else block has an if above it. If that if is no longer in the syntax of the program, the else will instead be paired with the one at the beginning and will run, because the command line check would succeed. So what about CBC mode can we do? We can move blocks around. So let's take a look at what happens to the plain text when we do an actual working implementation of that I'll show briefly afterward. So suppose we look at the script and we do three things. So in that usage statement, it used to say if a security error is detected, it terminates with a non-zero exit status or something like that. What has happened here is that block before the block that contained the triple quote, I just removed and put somewhere aside. What did that do? The next block that came after it is now corrupt, but it recovers after that. So one block was lost and one block became corrupt. Take that prior block and a second copy of the triple quote block and reinsert those in front of the else, so just after the if. And exactly what happens is that triple quote gets moved below the if statement and is now no longer code, the else will run. How would that code actually look to do this attack? Well, it's easy to do with DD, with all the skip and seek and count options. So a block in AES is 16 bytes long, 128 bits. So if you have an input file, an output file, you can copy the beginning and end verbatim and mess around in between. And that's basically what this does. This also is on that demo site. How would this actually, can we come up with a scenario where this might actually work? Possibly. Maybe we have some system administrator or developer with large numbers of cloud VMs or something, and they want a scenario where it reaches out during the boot process to run some script that has some routine system administration tasks that they want to be able to change. They put it on plain HTTP, they recognize that is dangerous, so they decide, let's encrypt it, so nobody can modify it, right? So they implement something in the boot process where we download an encrypted script over HTTP, decrypt it, and run it. One thing that people can be misled by is that OpenSSL has a command line utility that will help you encrypt and decrypt things. And like most command line utilities, it returns an exit status for success or failure. The exit status is based only on the padding being correct. So if someone just learns a little bit too much to be dangerous, they could be very misled in that, oh, it's still the same because the padding succeeded. Let's take a look at that actually happening. So suppose there's a man-in-the-middle attack where they substitute out the original script for this modified version that we just showed, okay? Say it happens normally, this boot process script runs. As that script was written, the if true gets hit and it prints out, detected a security error, you lose. Substitute out the modified version instead, now it runs the else. So no security problem detected, dangerous operation happens. Like the other one, the sample code is in this directory. So if you back up, there's actually a directory listing if you want to see all the examples. So another problem. Say you know, like, okay, I need integrity protection, but you implement some kind of integrity check that is not cryptographically secure. And now I'm getting into examples where I have some actual historical exploits where these were big problems. So I would say the most common misused security or redundancy check, cyclic redundancy check, is probably the most misused integrity check in terms of not defending against the right attack scenario. So CRCs, they're quick to compute, they're easy to implement in hardware. So, okay, we'll use that as an integrity check, right? The problem is that the system model or attack model of CRCs is called the binary symmetric channel. And this has to do with radios and wires and stray alpha particles and whatever else you might call it that might randomly flip a bit as it's being sent down a wire. So with some high probability, you send a 0, the other side sees a 0, you send a 1, the other side sees a 1. With some small probability, independent, and identically distributed, and all of those things, it gets flipped, right? Well, the problem is if there's a malicious adversary sitting in between, this is not random chance anymore. They can flip bits maliciously and whenever they want. So they can sit there and wait, oh, here's the checksum, or here's the permission level, and just flip it. More details about CRCs and where they're actually used and things to know about them. They're commonly 16 or 32 bits long. When you're in cryptography and you see something important that is 16 or 32 bits long, what does that mean?
Too short.
Brute force, right? Too short. So brute force attack. Say you have some system that takes messages and verifies the CRC and does something, you just blast all 2 to the 16th possible values and you'll get it if that's a security mechanism in that application. When someone says CRC, just the CRC, it's not the CRC as there might be the SHA-1 or the MD5. CRC is kind of a building block that needs more parameters. So a polynomial actually goes into there, and like AES and other cryptographic and error correcting code and so forth theory, there's Galois fields and polynomial reduction and so forth going on behind the scenes. In addition to that, so a certain polynomial needs to be picked. Implementations will commonly do some tweaks to try and prevent like CRC of 0 being 0 and other bad things like that. So they will often say do bitwise not of the input before processing it, or at a post-processing step like that, they have to decide whether the bits will be processed, little endian or big endian, and so forth. So I'm just mentioning those because the CRC, you might be misled, oh, attack doesn't work, or what I thought isn't true in this case. They may have just done something like this. The actual appropriate places for using it is as a defense against some kind of random corruption. So Ethernet, SATA, zip files, and hard drives are all places where it's actually used, but not in this attacker modification scenario. So say you ignore this advice and you use CRC for some security relevant purpose. Well, let's look at some of the problems with its properties. So starting out, I'm using a Python implementation built in just for ease of use. We take the CRC of the string hello world, we get a 32-bit value. The and constant there is to force it to be unsigned, so that's not important. So the CRC of hello world is some value. The bitwise not of that CRC is exactly what you would expect. First problematic property of CRC, what if we take the CRC of hello world concatenated with the bitwise not of its own CRC? Well, in the Python implementation, we get all 1 bits. Not something that's going to happen with random chance, right? If you saw a SHA-1 or MD5 of 0 or all 1s, that's not something that happens by random chance. So this is a big problem with CRC. As it cycles through these bits, there's a state inside that has like the current CRC of what I've looked at. If it takes the CRC of itself, it kind of resets the internal state to like 0 or 1, depending on how it's implemented. So not good for cryptography. Another problem, so given this ability to reset CRC whenever we want, say we take hello world, CRC of hello world again, we get a certain CRC. Now, knowing that we can reset it whenever we want, we can do that as many times as we want, and that allows us to produce as many messages as we want that all have the same CRC value. So this could come in handy if you're modifying something, right? How about some real world examples where CRC was misused? So everybody uses SSH, and there's SSH 2.0, and then there's this ancient SSH 1 that like nobody's supposed to use and is disabled and has all these problems. Well, one of those in SSH version 1.5 was that when it came time to verify packets are not modified, they said, well, let's use CRC. And this is actually an excerpt from the draft RFC document for SSH v1.5. It's basically saying you take some plain text message, you add some padding, you add an IV, or so forth, you encrypt it, but before the encryption, you take a CRC of the plain text and put it in that packet, right? So if somebody flips a bit, the CRC will be invalid. Well, when they redesigned SSH2, they recognized that as a big problem. This is from the OpenSSH website. Among the things they wanted to do was switch from CRC to a proper HMAC, or real HMAC algorithm, as they call it here, due to an insertion attack. So that sounds weird. An insertion attack in secure shell where you're like sudo this and sudo that, that could be a problem. So let's look into the details of that attack. It's actually, I guess, 17 years old. So here's a bug track posting for that. So someone actually was looking at SSH 1.5, I guess 4 years or so after it came out, and they actually found by combining some of these block cipher cut and paste things I showed before, as well as the ability to flip a bit, corrupt that block, but control the value of the next block when it was decrypted, they found they could kind of synthetically construct a packet containing some command by modifying an existing one and still have the CRC check out in the end by flipping bits and controlling what the CRC would be. So you can imagine you could inject like sudo rm-rf/ or something like that into the SSH command stream. Not a good thing. So that's why SSH2 should only be used, among other things. It uses real integrity checks that are cryptographically based. The other thing, in addition to kind of the collision problem, is modifying data that is protected with a CRC and being able to predict the effect that that will have on the new CRC of the modified data. So here is something as a stream cipher might do. We have some message XORed with some other message of the same length. So I have hexadecimal and ASCII. So all B's XORed with all A's produces pound signs. In this scenario, we take the CRC of both of those incoming messages, and then we get the new message. Now the question is, without actually taking the CRC of all the pound signs, could we predict what that value would be given only the CRC of X, the first message, and the value of Y that we're XORing against it? Right? So we actually could do that. We end up with the CRC, if we compute it explicitly, is this 7F95 so forth. And then in the Python script underneath, you can see the CRC can actually be computed without looking at X. You take the CRC of X, XOR with the bitwise not of reset the state and all the A's. So in other words, take a message, tamper with it by flipping some bit. As long as you do the correct thing to the CRC, it will still check out. Well, what if that X value were actually unknown to the attacker or only partially known, but they still know the CRC? Well, that could be a problem. Or alternatively, what if both that original X message and its CRC are encrypted using a stream cipher? Well, stream cipher, we can still flip bits wherever we want. And that brings us to an infamous security problem, which would be WEP. So remember WEP 802.11, 40-bit, IVs, too short, injection, so forth. So how the WEP frames actually looked: they sent a frame containing an IV and then RC4 encrypted data composed of a message and its CRC. So some researchers, basically from like 2000 to like 2010, and I guess nobody cares about WEP anymore, but basically it was one attack after another, each one improving on the last. One of those earliest papers was recognizing the fact that looking at these two properties, XOR on ciphertext does the same thing to the plaintext, and we can fix up the CRC after modifying it. They gave a much more precise and theoretical description of exactly that, basically saying we have a message and a delta, or changes to that message. If we take the CRC of the message, the CRC of the delta, and do everything exactly right, we can produce a new message based on an old one, having never known the key. So that led to many things. The most one matching up with this particular vulnerability being the Cafe Latte attack, which someone actually presented at TorCon like 6 years ago or something. But basically they recognized that rather than doing typical approaches to breaking WEP, which is I'm standing here, the access point is there, let's interact with it and get it to generate lots of IVs, they took the opposite approach, which is corporate Windows laptop leaves the company, like somebody goes on vacation or to a conference. They noticed a property about the versions of Windows at the time where there was this remembered network list. It would like reach out actively for like, where is this network? Where is this network? You could pretend to be the access point, And then they noticed a couple things, like it would send out an ARP request upon connection, which you couldn't answer because you didn't know the key, or maybe you could because using this malleability property and the ability to compute the correct CRC, they could flip around the correct fields in the message to send a message to that device, and every time it would respond with like an ARP response. And one of the properties of WEP is if you have 2 to the 24th packets, because of the IV being 24 bits long, then with increasing probability, you've seen all of the IVs and all of the key streams, and then can take advantage of various biases in RC4 and recover the WEP key. So this is like the nail in the coffin for WEP if the other 50 attacks before it were not. So that's a problem with CRCs. Now, say your developer knows, okay, cryptographically secure one-way functions or cryptographically secure hashes. Wonderful, let's use that. Well, what if they forget about the fact that these typical functions are unkeyed, or in other words, have a message, just like CRC, anyone can compute the hash of it as well, right? Well, one of the problems if we take our CRC approach is the guarantees and properties of even unkeyed hash functions, which are the famous 3 here that are always confusing and trying to remember what the distinction is. So collision, preimage, and second preimage, which basically boil down to you can't find 2 messages with the same hash value for one, and also given a hash value, it's computationally infeasible to generate some message that hashes to that value. Or at least when the hash function comes out, it meets all of those properties. But moral of the story, this whole idea of flip a bit and like somehow fix up the hash value is not going to work unless it's catastrophically broken in some way. So we have to find some other attack or look at even worse programs than before. In this one, I'll actually look at something behavioral. So who has ever downloaded a Linux distribution? All right, maybe using wget or something in the background so it doesn't crash or you accidentally close the tab or whatever, right? And you might use HTTP, or if you're old-fashioned, FTP or something else, right? And once it finishes, you don't want a coaster, so you want to verify that the image downloaded correctly. So you take a look at a file that looks like this, right? So SHA-256 sum, you compute it locally, see if they match, and if they match, you're good to go, right? Well, if your attack model, or threat model, as you call it, was about random corruption to that image as it was downloaded, fine. But one of the other reasons why they produce these is that if you think about it, there are large numbers of mirror sites that they just kind of transparently send you to. If you think about certificate authorities having like 50 people that are all trusted to do the same thing, maybe not so good of an idea. So if you think about a compromised or malicious mirror site, this may not be good enough because they modify the ISO, they can modify the hash file as well. Well, this is not something that they overlooked as Ubuntu or Debian or Red Hat, whoever. The property that Ubuntu and Debian actually do is they put the signature in a separate file that looks like this. So of the people that download Linux distributions and compare the hash, who actually remembers to verify the signature of the hash? Not so many, 1. Okay, so that's important. This was just a behavioral example, but anybody that implements in their software some kind of auto-update feature, I've often seen it's file and hash a file and you're good to go. They don't think about, well, if you're a burp suite or whatever, I can just put whatever hash I want. So that's important. You need to think about not only is the hash correct, but who's capable of generating it. Say they do recognize that. We want to produce a keyed hash or keyed one-way function, which is a message authentication code. But some people think of that and they decide, let's make our own. Let's take a key and a message, combine them in some way and hash them. Well, quickly, what a message authentication is supposed to do is just like a hash, except there's a key. So only someone in possession of a key can generate that hash. But don't forget, only someone in possession of that key can verify it either. So it's like symmetric cryptography as opposed to asymmetric cryptography. What a MAC does, protect a message from being modified. A lot of people see MAC and just immediately think of HMAC. That's probably the most popular way because of various RFCs and IETF standards, but it's not the only way to implement a MAC. In fact, it's kind of a passing thing if you look at some of the newer cipher suites that I'll get to later in TLS and so forth. But a hash is probably, in isolation, one of the fastest ways. So it's often the one you think of first. Don't confuse them with digital signatures, just like the previous example. So it's symmetric. This mass software distribution would not be a place to use an HMAC because you would have to have the key to verify it, and you have the key, you can modify it. Don't try to make your own. So how can you fail? Well, it turns out that all three of the immediately obvious approaches for constructing a MAC are insecure, some worse than others. So basic problem, you have a key, you have a message, you want to hash them so that you cannot generate that hash without the key. Well, first one, maybe you take the message and you concatenate the key on at the end. Well, the problem there was if you actually want an HMAC to be secure as any other form of MAC, suppose the hashing algorithm has a collision in it, that approach would be broken because of the layout of the message coming first. But it's not so bad necessarily. The one that is worse is the second example, key concatenate message, and I'll get to why in a second. And then actually the people that really care about these things, say you have two keys and you do a key, the message, another key, that can be shown it's no more secure than one key. So all three of these are not something a cryptanalyst would think very highly of. But the middle one is catastrophically broken. The reason is because of a length extension attack. And the reason for this, when you have a hash value, that hash value represents the internal state of that hashing algorithm when it was done processing the message. If you can take that state and put it back into the hashing algorithm and feed more data through it, the key's already been through, so you'll compute a correct hash. In a real world scenario, the key is unknown, but you might know its length, 6 bytes in this case. Hopefully it's actually bigger than that. And let's observe that we're interacting with some system that we are able to convince it to do the HMAC of the string hello world, and it returns this value, and it uses MD5, which MD5 for HMAC is not considered broken, unlike raw MD5. Just an important point. Now, can we use a length extension attack to somehow feed Earth, Mars onto the end of hello world and still be able to compute the MAC without knowing the key? Almost. So as stated, you have a hash, you can put that back in and keep going. The problem is that MD5 and SHA-1 and SHA-2 share a property where they, like a block cipher, actually have a block size. They don't just go like bit by bit or character by character. And knowing the property of MD5, you have a message. Before it hashes it, it concatenates a 1 bit or a 080 byte, fills it in with 0 bytes to meet a boundary on the block size, and then, or just before it, and then adds to that the length of the message in bits and as a 64-bit little endian integer. So the length part is important, otherwise you would have the padding added and different strings could end up with the same post-padding representation. Notice, though, that the consequence is this is because MD5 only operates on a certain block size of 64 bytes. Knowing this, going back to our problem, we don't know the secret, but we know it's 6 bytes long. And if you do this value on hello world, you end up with knowing that internal state contained this as the hash was generated. The first 0x80 is that 1 bit. The second 0x80 is the length of the string hello world in bits. How do you reconstruct the state? Well, this is one of those corner cases that I always find where scripting languages make it more difficult than C. So in OpenSSL, you can actually take that hash and just force it into the struct context that it keeps around for maintaining the internal state of MD5. So we take this 128-bit long hash, and after looking at the RFC or Wikipedia article of how MD5 works, you know where the various values go, and you know how to reverse the bits or bytes in the correct order. The NL is just keeping track of how many bits of message have been seen. So we've put that state back into MD5, and we can feed more things through it. Let's do exactly that. Run that Earth Mars through there, and MD5 final will add the padding again and release the hash. And we notice we run that program and we get this 16, 15, and so on hash. What this told us is the hash of this synthetically constructed string underneath of hello world, padding, Earth, Mars, and in reality, padding again, is that value. So we can check that out by manually taking the MD5 of this string and seeing if we get the same value, and we do. So that's a length extension attack. Similarly to the other problems, some sample code there if you want to play around with it. The important thing to note is it's not just MD5. SHA-1 and SHA-2 have the same property with different block sizes and maybe different byte order, depends on who designed it. But this is something that NIST and others actually took into consideration as they designed SHA-3, and it's not susceptible. And the only distinction is if you don't reveal the entire state of the hash, you can't like rewind and go back into that state and continue. So this seems like something, who would ever make this mistake? Well, Flickr did, which may have been more important when they made the mistake than they are today. So I think they're associated with Yahoo or something. So they had an API, which kind of, if you think about Amazon Web Services, they have this idea of a signed URL, which in reality should be called a MAC'd URL because it's not asymmetric. But they had some URL where you call an API and you have a bunch of parameters saying like user ID equals this, action equals that, maybe photo ID equals something else, and then a hash value so that you could hand this, as a web application, you could hand this URL out to a user's browser. They could reach out to the Flickr servers, and those servers could in turn verify that the user and application, everybody's okay with this, and it's not just some random URL that you're brute forcing. So they had an API that looks like this. I have the paper at the bottom linked. But the moral of the story was they were able to do the length extension attack, combine this with some properties of HTTP query strings, as well as the way in which they computed the hash to have a URL that looks like this. And you can't really see because of this projector, but where I have the MD5 padding, it's very similar to what I just showed with a 80,000,000 and then a length. And then they were able to have essentially the original request padding and then more data added on the end that did something completely different than the original one, and the server accepted it. So this is a big problem, but if you just use standard algorithms like HMAC, you would have been fine. So kind of embarrassing for them. Another problem, as these systems we're thinking about get more and more sophisticated, say you are indeed doing encryption and authentication. Well, the problem you have is what order to do them in, right? The two systems that use CRC, it was integrity check and then encrypt. Well, it turns out that if you think about the three ways to do that, modern practice is you do the encryption first. And whether the others are insecure or not depends on the specific protocol you're looking at. But they're called encrypt then MAC, which is as it sounds, you have message and its hash or other integrity check and encrypt the whole thing. And then, or that's MAC then encrypt. Encrypt then MAC is you would have the, okay, this is very confusing as you can see. So encrypt and MAC versus MAC then encrypt versus encrypt then MAC. So do you encrypt the hash value or not, and do you do it before or after encryption is what it boils down to. And the encrypt then MAC is what is recommended today. The problem with the others is the issue of padding. So if you hash or integrity check ciphertext and then encrypt or if it's plain text and then encrypt, that plain text actually changed a little bit in the process of encrypting by adding padding. So block ciphers have to do this. Only in encrypt then MAC, because the encryption happens first, is the value of the padding covered by the authentication check. And all the others, you can tamper with it, and the check will still pass unless the padding itself fails. But what if the padding itself is not very well defined, and it's not covered by the HMAC? And you can flip bits or cut and paste blocks around. If this starts to sound familiar, this is actually Poodle, the kind of stake through the heart for SSL 3.0. The actual root of the problem is CBC encryption. Unlike the actual RFCs that have come out since that protocol existed, the padding block, which is 16 bytes, was defined that just one single byte in there had to have the size of the padding, right? Well, what they noticed in that paper is by taking advantage of these CBC attacks and kind of controlling values before or earlier in the process and just cutting those blocks away and putting them later. You have this single byte that has to be correct, and by random chance you have 1 and 256 of matching. And if you match that, they were able to go byte by byte and reconstruct values of session cookies and so forth. And once you do that, despite it being over SSL, now you can just go to the application directly and be that user. However, if they had authenticated that padding by using encrypt then MAC, they would have been okay. So minor little detail like that is why, that's why I say this seems a little more interesting than just encryption alone oftentimes. And the secondary thing, you thought an integrity check was for integrity, but in this case, it actually helped you out with confidentiality as well. Looking at the other purpose of integrity checks as I get ready to close out here. So the other thing that kind of falls out of the design of an integrity check that's now used almost universally is you want to verify that a message you receive today and a message you receive a year from now are the same without storing it, which is exactly the problem you have with passwords, right? But all the immediately intuitive ways of doing that are insecure pretty much. So you might, by looking at a hash function, say, okay, one-way transform, great. You can go one way, you can't go the other. So you take a password, password 1, you hash it, and you get a hash value, and you throw that in a database. Because of preimage resistance, this wonderful property that we studied of this algorithm, we know that taking that hash and figuring out what the password was is infeasible, right? Well, if the user used a weak password, every common password is already out there as its hash has been pre-computed in a dictionary. Disk sizes are large enough to store very common words or even less common words. You Google an MD5 of something that's not cryptographically secure or not a good password, it's going to come up in one of these sites. So this is, you'd think this would be a solved problem, but if you look at kind of these niche market web applications that we see often, like this has not been realized and fixed even today. And I actually want to mention the LinkedIn breach like 2 or 3 years ago. I think they had plain hashes. And I'll get to the correct way a little on. So given all those failures, what are the actual tools that we covered and what are the guarantees they provide in a little more detail? So I kind of covered one-way functions or hashes. They're not the only way, once again. You take a message, you get an integrity value. Message authentication codes, a keyed version of that. Authenticated encryption, I'll get to in a little bit, and digital signatures. So one-way functions, you take a message, you get some transformation of it that can't be reversed. Hashes are not the only way to do that. And another way is you can take a CBC mode cipher and kind of manipulate it in a certain way to get what you might call a hashing algorithm. Remember those properties. I don't want to reiterate them again because they just confuse me and you, most likely. Maybe not everybody. But I think a notable property here is, unlike symmetric encryption, which we still have plenty of things from the 70s and 80s that are failing because of key length, rather than other properties like triple DES or something, or even RC4s kind of just in the past few years been like unusable. They tend to catastrophically fail not very long after they come out, I've noticed. So MD4 still has some residual uses in some NT password things, I believe. And then MD5 and then SHA-1, all three of those are like do not use at this point because of collision problems. So if you think about it, like SHA-1, something coming out in the mid-90s and 20 years later considered like completely unusable, and it's reputable people that came up with these things. It's obviously much more difficult than just a plain cipher. So recommended today are SHA-2 and SHA-3. SHA-3 is more recent and may not be in all the libraries that you would use. SHA-2 can be a little confusing because SHA-384 is considered a 384-bit long version of SHA-2 and not SHA-3. If you need to implement message authentication codes or use one, remember that it's not just adding a key to a one-way function. HMAC is probably the most popular. It's not the only way. Don't build your own. if you look at the implementation of HMAC, it's actually a hash inside of a hash with these weird constants added in there for various reasons that theoretically give you certain guarantees. So don't tamper with that. And an interesting point, as I mentioned before, because HMAC is so well-defined or well-designed, even if a collision is found in the hash, the HMAC might not itself be broken. And this is something that's a little important to me because I write recommendations and reports. Say they're using HMAC MD5. Well, this is not like critical places on fire. You can say there are RFCs out there that are kind of like halfway on the point, like updated considerations for MD5. And if you search for that, you'll see it. But it says like HMAC MD5 is not necessarily broken, but in the spirit of deprecating algorithms when they're weak. Like it's a very weak statement like that. HMAC SHA-1 is considered like good to go still. So as you look at that problem, what if you could encrypt something and authenticate it in one step that's difficult to do incorrectly? And that's the idea behind authenticated encryption. And part of there, that's less opportunity for mistakes if the encryption process is a black box API to the developer. And this is the mindset behind AES GCM or Galois counter mode, in addition to some others that are less popular. And the reason this is important is particularly for best practices in TLS and SSH. Both of those offer GCM and modern versions, and that's the best way to go because the whole historical order of MAC and encrypt just goes away if you use that. It's also faster than doing the two as separate steps. So that's important when you think about AES-NI and other performance improvements and making sure you get 100% of the benefit of those. Final review on digital signatures. It's basically a MAC but asymmetric. So anyone can verify it, but only one person can generate it. The important thing though is that these use one-way functions like hashes in their raw forms internally as part of that process. So a RSA certificate has a SHA-256 hash of things inside it. So if the collision is found, unlike HMACs, the whole system goes away. So MD5, this is like 10 years ago at this point, you can modify a certificate and reconstruct the hash and break TLS or other system in that way. When you think of digital signature, think of RSA and ECDSA, two most common implementations. So closing out. As a developer or security person, what should you know about these things if nothing else? And that would be the recommendations. So if you are developing an application or just as an end user, you run into a situation where you're doing something security relevant that requires message integrity. If you're making some system that has multiple network nodes or IoT, since I'm from the IoT village, just use TLS if you can. Or maybe use SSH if that's more appropriate for what you're doing. Don't design your own. And if you do insist on designing your own as a blank slate today, really look at AES GCM mode for performance and these stronger and more difficult ways of messing it up. On the other side, if you're doing passwords, don't say, well, we'll MD5 this and our salt is this. Just use one of these built-in algorithms like PBKDF2, bcrypt, scrypt, and so on. They're actually designed for deriving a cryptographic key from a password, but you can use them for verification as well. Current recommendations are enforce a minimum length and perform a dictionary check. This is actually things going on with the NIST SP process right now, where a lot of the old wisdom like password aging and so many exclamation points and security questions on all that is actually not just security people frustrated with that, the actual government standards community is starting to realize that and move away from it as well. So, closing out at 49:57, any questions? Okay, so I will have these, they're not on our ISE website immediately, but I'll get them there sometime tomorrow. And in the meantime, if you go to demo.securityevaluators.com/integrity, you can play with some of those examples if you so desire.
Thank you very much.
All right, thank you.